Welcome to the mind of a math teacher.
Hey, it is a beautiful day to practice the quotient rule for logs. So here we go. My goals are first to talk about what is the quotient rule for logs, and then to go through some examples of using it at different levels for you. So here we go. The quotient rule for logarithms is down here at the bottom of the screen. It says that the log of a division, like b divided by c, can be converted or expanded into two logs that are being subtracted from one another. And notice that the top value, the numerator, has to be in the first log, and the denominator, the bottom, has to be in the second log. So we can expand the log of a division into log of the top amount minus log of the bottom amount. And also notice that the bases have to be the same on all of these. So this is a good rule to learn, a good rule to be able to use. And we also want to be able to go in this direction from left to right, expanding, and from right to left, when we start with the subtraction of two logs that have the same base, we should be able to simplify that into a single log with a division using this quotient rule. If you haven't seen my video on the product rule for logarithms, I would recommend that. We are going to also be using the product rule in some of our examples. So here's my first example for you today. It says expand log of x over zy. And you want to notice right away that we have a quotient overall, log of a quotient, and that this is a base 10 logarithm. That happens anytime that the base is not showing. It's called the common logarithm. So in order to expand this, we just want to use our quotient rule first. We'll say log base 10 of the top minus log base 10 of the bottom. But then you hopefully notice that there's a product right here, so that we should now use the product rule. So the thing that we have to be careful in rewriting this is we have this minus sign that applies to the entire amount log of zy after it. So in our next step, we're going to say minus parentheses, and then we'll do our product rule. Log base 10 of z plus log base 10 of y. Now, because all of these are log base 10s, we don't need to continue to write them, but we could write it one more time, distributing the minus into that parentheses so that we have log of x minus log of z minus log of y as our final answer. And that is fully expanded from what we started with. Our second example. This one says rewrite as a single logarithm. So in this one, we're going to be going the opposite direction on our rule. We're starting with logs that have minus signs between them, and we want to turn this into a quotient. There's a reason that I have this example second, right after looking at that previous example that we had. Did you notice in the previous example that these two objects were on the bottom of the fraction, and this one was on the top? So let's go through how we can rewrite this as a single logarithm, essentially doing the process backwards that we did in our last one. So here we have log of 9, and what I'd like to do is factor out this minus from both of these other two logarithms. And after seeing that first example, I think you see how this is going to be a very good way to go. To think of this in terms of a product rule that needs to happen first, and then we'll do the quotient at the end. So using the product rule, we would have log of 18 times 3, which is log of 54. And here we have log of 9 minus log of 54. And now we can use the quotient rule, log of 9 over 54. And this will reduce to log of 1 over 6. And that is our final answer. So notice that we factored out the negative sign at the beginning so that we could do the product rule on these second two, and then we could build our answer. In our third example, we're going to expand this log base t. It doesn't really matter that this is log base t instead of log base 10. This will work with any base, as long as the bases are the same on your logs throughout the question. So when we expand this, we'll just get log base t of 11, doing the top value first, minus log base t of e on the bottom. Notice on this one, I'm writing base t on the logs on my answer, because these are not the common logarithm. They're not base 10, unless, of course, t equaled 10. But it doesn't necessarily have to be that, so I have to write t on my answer. Example number 4. This time we want to simplify this expression, which is slightly more complicated. But after seeing example number 2, hopefully your first thought would be to factor the -1 out of those last two terms so that we have a product rule. So let's do that. We have log of e to the 7th minus, that minus being factored out, we would get log of e plus log of 5e. And our product rule would make this part log of 5e squared. And now we can do our quotient rule and get log of e to the 7th over 5e squared, which will simplify because we have an e to the 7th on the top and e squared on the bottom. So an e squared will factor out and simplify from both of those. So our final answer will be log of e to the 5th over 5. And we have expressed it as a single logarithm. Example number 5 coming up. So on this one, again, we want to expand. And hopefully after seeing multiple of these examples, you can sort of skip steps, and you can see that since we're dividing by the u and we're dividing by the v, in each of our examples, we've ended up with a minus for each of those things that are on the bottom of our expression. So that way, sometimes, once you get used to certain structures of logarithms, you can jump to the ending, as long as you understand the steps of what's really happening here is factoring out a -1 or distributing a -1 in, depending on the way that you're going, and you're actually using the product rule to get this. We've jumped some steps in this example. All right, here's our last example. All right, number 6. This time we want to prove an identity for logarithms. And it's very important that when you prove an identity, you don't just do all of your normal algebraic steps. I like to make a rule for myself that where this equals is, I can't cross that line, meaning I can't add something to both sides to get rid of it on one side. I can't subtract on both sides. Any of those kind of operations are not what we want to be doing. We just want to simplify each side, and that way we can show that if we get the same thing when we simplify both sides, then these truly must always be equal. So without crossing over this line at all, let's work on the left side first. As you saw in those examples that we just did, this could be rewritten as log base 4 of 10 on the top and 18 times 4 on the bottom. Well, this will reduce to a 5 on the top and 9 times 4 on the bottom, which is log base 4 of 5 over 36. And here, of course, we started with log base 4 of 5 over 36. So this has been proven. So if you like this video, it helps me out. It helps it get in front of more people. I think that's the way YouTube works. If you comment on this video, then that helps you because it will show me what other videos you'd like me to make, things that you'd like me to answer and help you understand. And if you subscribe, it also helps you because then you'll get these videos much faster. You'll get them as soon as they upload and you'll be notified of that. So have a great day and keep on learning.